we're going to focus on intermolecular forces. So remember, an intramolecular force is the force in the bond. So that's looking at the hydrogen to oxygen bond in water. Intermolecular forces is the force between two molecules. So here we're looking at the attraction between the hydrogen of one water and the oxygen of a different water. So make sure that you read the question carefully so you know whether you're talking about the bond or you're talking about between molecules. Now, intermolecular forces depend on two things: the polarity of the molecule and the size of the molecule. Generally, the larger the size of the molecule, the stronger the intermolecular force becomes. But before we looking at the size of the molecule, we always determine the intermolecular force based on the polarity. Then if they have the same intermolecular force, we look at the size. So there are three types of intermolecular forces. The first is London dispersion force. These are for nonpolar molecules. And in a nonpolar molecule, the electrons shift to one side of the electron cloud and cause a temporary or instantaneous dipole moment. It doesn't last very long, but it can induce a dipole moment in a molecule nearby. So in the picture here, we have a nonpolar molecule. The electrons shift to one side of that molecule, so it becomes delta negative for an instant, which could then cause the electrons in the neighboring molecule to shift to the opposite side. London dispersion is our weakest intermolecular force. As molecules get larger, the strength of the London dispersion force becomes stronger. So iodine has a stronger intermolecular force than fluorine does. They both are London dispersion forces, but because iodine is larger, that force of attraction is stronger, which explains why iodine is a solid at room temperature where fluorine is a gas. So that's the only force of attraction for nonpolar molecules, and our nonpolar molecules then have low melting and boiling points and are usually gases at room temperature. A dipole attraction is within a polar molecule, and it contains a permanent dipole moment, meaning there's definitely a positive and a negative side of your molecule always. The strength depends on the distance and the orientation of the dipoles. It is stronger than the London dispersion forces, so it has a higher melting and boiling point than those with just London dispersion forces. And it can occur between different polar molecules. So you can have a dipole moment between water and ethanol. Even though they are different molecules, they're both polar. Van der Waals is used to talk about both London dispersion and dipole-dipole. So it's like an umbrella term that covers both of those. You can have those instantaneous moments like in London dispersion. You can have induced dipole where one molecule is causing the other molecule's electrons to shift. You can have an ion-induced dipole, meaning you have a cation and it's interacting with water, and so water's electrons are going to shift to the side that the positive is on. So there's different versions of van der Waals. Hydrogen bonding is the strongest force of the strongest intermolecular force. It is actually a special class of dipole-dipole. It's when there's a hydrogen atom and a very electronegative atom. So those atoms that are very electronegative would be fluorine, nitrogen, and oxygen, and you can remember them by remembering FNO. It's a strong type of dipole-dipole moment. The boiling points then are significantly higher, even if we were just to look at the mass and think about the dipole moment, they're even higher than what would be expected. Water is the strongest type of hydrogen bonding because of its geometry. So it has that tetrahedral shape, electron domain tetrahedral shape, and so it has two lone pairs in the oxygen. So the oxygen could hydrogen bond twice as opposed to like methane, which the nitrogen only has the one lone pair. It can only hydrogen bond once. Water's solid state holds the molecules in a fixed distance apart, but it has a lot of space between those molecules, which is why the solid state is less dense than the liquid, and so our ice floats in the water.